Okay, today we're going to be talking about LED lighting technology. We're going to be covering the basics. We're going to try and understand equivalence, and we're going to look at efficiency and lifetime claims. So what's the motivation behind all the changes that are occurring in lighting and the advent of LEDs? Well, I guess the 1997 Kyoto Climate Change Protection Objectives have defined a set of requirements for us to prevent climate change, but the EU has mapped those onto what it calls 20-20-20, and all its legislation, all the things it's working on, are all designed to deliver that. Lighting has a strong part to play in this. Mostly they're banning inefficient light sources such as incandescents, and there's going to be a phased removal on the market of those. And of course, this is underpinned by the fact that LEDs are becoming very much more efficient, so they're seen as a replacement. Very shortly, LEDs will become the most efficient light source there is available. And then, obviously, as that efficiency roadmap continues, then we expect there to be almost no incandescents on the market for the time. Part of this, I guess, the underpinning part of the McKinsey report and everybody else's market forecast is we've got to actually hit those efficiency roadmaps. And actually, we're very strongly on track on those. So the latest CREE R&D number is 276 lumens per watt for a 1 watt LED, which is incredible. That's actually slightly ahead of the US DOE roadmap that underpins this. It shows that LEDs are going to basically take over. And as a result of this efficiency that's now proven, LEDs are the future of lighting. Okay, so we're going to now talk about equivalent light output. This is pretty difficult because it used to be that everybody was happy with light bulbs are measured in watts, and you've got you've got a 50 watt or a 70 watt or a 60 watt, and you knew what that meant. Now it's quite key that we look at a different set of metrics to measure, because you can no longer, the quality of lighting is no longer measured in watts, it's actually measured in lumens per watt, and the output needs to be measured in lumens to do a certain task or a certain replacement. So there we go, that's the key part. So electrical power consumption in watts is a way we're defining it, but really we need to be looking at lumens per circuit watt as the key number. And as the situation is changing so dramatically with LEDs and the efficiencies are improving by about 15 to 20% a year, and prices are dropping by about 15 to 20% a year, that's for the LEDs themselves, then it's pretty key that the world needs to change its way of measuring lighting. Okay, difficult to know exactly what historical light bulbs used to do or lamps used to do. One of the big challenges I've seen is that people will go, oh, a halogen light, a 50 watt MR16, well, halogens are 25 lumens per watt, so I've got 50, so, that's kind of like 1,000-ish lumens and more, so why aren't you producing 1,000 lumens from a 50 watt? Actually, halogens aren't that efficient, and Selmer and ELC a number of years ago conducted, and these are the manufacturers' federations, and the testing was done by the big guys as well. Basically, they tested these things, and they kind of concluded that things weren't quite as rosy as they perhaps led everybody to believe in a theoretical way. So a 50 watt MR16, which is listed here, has useful lumens, i.e. in the directional cone here, of 600. So that's way lower than, I guess, you would guess by timesing 20 by 50 and getting 1,000, or 25, 50, and getting a lot more. So you've got to be really careful here, because it's important to actually work on measured data. So the Selmer ELC data really is the benchmark for all our equivalent standards. By the way, Selmer and ELC merged this year to become Lighting Europe. Comes in when you're talking about on-axis brightness. And very often what will happen is an LED manufacturer might use a very narrow beam, say it's 30 degrees, it's actually 24, quote an on-axis brightness number, which is equivalent to a 50 watt GU10. Well, to the beam angle matters here. So this kind of levels of equivalence are important. For illumination and actual physical quantities of light, the lumen number is key. If you're doing task lighting or spotlighting, then clearly on-axis brightness is important, but be careful of this misleading position. It's something that you will see a lot in the market even now, and very prevalent amongst the slightly less scrupulous manufacturers or importers. Okay, let's move on to the next slide. So let's take a look at a couple of little examples here. And this is our 2011 catalogue data. So obviously, as the new catalogue is produced, things will change. Let's take a look, and I'll put a little marker here against LED lumens. So a Titan, well, let's take a Mercury 630. That's delivering 629, well, sorry, it's LED lumens, i.e. the lamp lumens, if you like, are 629. So that's actually equivalent to a 35 watt MR60. And if you go back to the previous table, you'll see that the 35 watt MR60 produces 600 lumens. Now, that's just the lamp. So we need to consider the beam angle to get our sort of effective application here. And we also need to consider the delivered lumen, i.e. the loss associated with the light source by putting in a fixture. We will give the lamp lumens, if you like, or the delivered lumen, the LED lumens, plus also the fixture delivered lumens at the end here. Let's move on and see what I'm talking about here. So this is where we get into a conversation about, are we comparing apples and oranges, or are we comparing lamps and hall fixtures? So let's talk a little bit about those. Well, typically lamps will last a little bit less time than fixtures, because you're constrained by the history of the form factor, if you like. There's a technology here, LEDs being forced to fit into a footprint designed by a different technology, and that's tricky. So as a result, you're going to make some compromises in, say, a directional lamp here, in that it's going to either have to be a bit bigger, or it's going to have a little bit less light output to deliver what you actually need. So as a result, generally people will push the envelope on all parameters here, and typically lamps will be 3-year warranty. And if you remember in the LED Basics presentation, the big worry, of course, is putting the drive electronics in with the LED in that footprint. It's a little pressure cooker, and the weakest link in there will be the capacitors. So that will cause cheaper lamps to fail way quicker than the LED itself. Now, things have moved on a little bit from this number here. Lamps are now at about 400, 450 lumens directionally. But again, some of them are getting a bit too hot, so they might not last as long as you think they're going to. That might result in shift in color quality. It might reduce in terms of lifetime as well. So I think the point is you have more control over the envelope with a dedicated fixture, so you can get the thermal management right, which is going to give you increased lifetime, increased efficiency, and reduced color shift. Now, that's the case for Photon Star LED luminaires. We've designed these things with a level of understanding that I think is second to none in the market. However, it's not the case with every single luminaire, and we see some shocking products on the market almost constantly. And sometimes the heat sinking is massively inadequate. I think there was a recent job where we lost something to a fixture, a dedicated luminaire kind of thing, and it was the heat sinking was probably only capable of heat sinking a third of the power fitting did actually produce. So there was a big risk here that this wouldn't last, and actually when we tried to test this in the lab, it was broken, so it kind of burnt out already. So the key thing here is dedicated luminaires have the ability to actually manage the right output levels of light, plus also the correct levels of thermal management as well, to deliver the lumen package and the beam angles and the parameters that the customers care about. The lamps are catching up fast, but they're by no means perfect. You're making compromises on one or two parameters to get a good one. I think the one shown here is a Philips Master lamp, probably one of the best lamps on the market. Although, let's be honest with everybody here, they've had 2 major safety and recalls over the last 3 years for this product range. So, it's by no means easy to get right, I think, is the point we're trying to make. Okay, so let's take a practical example here. I guess if you look at this delivered lumen number, and this is obviously a little bit out of date, as I mentioned, but I think the message is very clear here. To get the same levels of illuminance on the work plane between a Ceiling Star and a particular branded GU10 7-watt lamp, you needed, so they're the levels you can achieve with the lamp, 152 average lux, 130 with the Photon Star product. And by the way, this is the 2011 data. You need 9 fixtures to do that. You need 25 with the other lamp. So are you really getting everything you need here? And actually, is the total system cost correct for the application? And very often we've got some strong advantages here when you look at the whole solution and the delivered cost of the solution. Okay, fixture design and efficiency. LED systems. This is a particularly complicated slide, but really what it's trying to say is there's a lot of stuff in there that is immediately obvious to anybody. And, oh, it's just an LED. Well, look, in designing an LED chip, you've got all sorts of efficiency factors. You've got quantum well, you've got the phosphor efficiency, and you've got the electrical efficiency. I mean, there's just so many. And a lot of things can go wrong in there. So let's take an example here in this blue box. This is where most of the things can go wrong. So the LED chip might not be very good. The phosphor, etc. We can cook it. Of course, we've discovered overdriving them and running them too hot will cause the thing to fail more quickly. But you can see a lot of things need to be thought through, even at the chip level, to get it right. So that's one of the reasons why you need to know where the chips come from. And obviously, at Photon Star, we only use tier 1 manufacturers' chips and packages, and that's pretty key for getting the rest right. Now, you can get it wrong on any other place as well. I mean, we talked about you can get it wrong by, doing a bad job on the luminaire housing. You can do a bad job on the power supply. So I guess at Photon Star, we start by using good LED chips from reputable manufacturers. We mostly favor people like Cree, Lunalabs, LG, and Sol Semi, but mostly I guess we focus on Cree because they, I think, are the innovators and leaders in the efficiency targets. So the message here is it's complicated. Don't worry about it, but just be aware it's complicated. So we talked about thermal efficiency, thermals in terms of lifetime, but actually, there's a reason why you would want to make sure you've well engineered a fixture, and that's because if your junction temperature goes much above 85, there will be a reduction in efficiency. In fact, actually, if you go above 25, you get a reduction in efficiency. So take 25 at 100% light output. If you then run that up to 85 degrees C junction, you're getting 83% of the light out compared to at 25 degrees C. So things get a little bit more extreme once you get past 85 degrees C, and we start to see the efficiency roll off just a little bit further because the straight line graph actually goes a lot quicker in some LED. So very important to get it right. Obviously, heat sinking is the key to good thermal management and making sure your LEDs are actually connected to the heat sink. Now, I've heard quite a few people come up with all sorts of stories about heat sink. The reality of the situation is you want to be keeping your junction at 85 degrees C. That could mean if you've got a very, very good thermal path between the LED and the heatsink, you could be running the heatsink in the 60s. Either way, if the heatsink's too cold, i.e. it's a small cold heatsink for the power, then it's probably not in contact with the LED. If it's too hot, and certainly if you can't hold it comfortably with today's LEDs, I'd be concerned that fixture or that lamp was not going to last. Particularly in the case of a lamp, if it had the driver included in it, that would be a worrying starting point. But you can see, if you want to get the best out of your LEDs, you want to keep them cool, There are other factors too, such as colour shift, which get worse as you move above junction temperatures of about 85 degrees C. So efficiency falls off, colour shift becomes a problem, and additionally the lifetime is dramatically reduced. So here's a little chart just showing that we're on our fifth and actually generation of CS5 light engine inside ostensibly the same heatsink. Look what an increase in light output has occurred. Look how the power consumption has dropped, and look how the efficiency has increased. So this is since 2008. The lumens per circuit watt has gone from 40 up to the 213 range, up to 96. So that's a massive improvement. All within the same form factor, all delivering, if you want, equivalent levels of light output. So we have an entry level one now, and we have a mid-range, and we have a high performance one. Originally, when we introduced the CS5 range, we really only had one, which was the one that could just get over the bar. But now, I guess with improvements in LED efficiency, we're able to offer a more comprehensive product range. Okay, so source numbers. I guess this is something I probably would say is quite key. It's all very well to look at the light engine number or the LED number or the actual lamp number, but it's actually about fixture efficiency as well. So I guess what here is called the light output ratio, or LOR, 0.9, 90% efficient. So therefore, if you look at, say, traditional incandescent in a fixture, you might find that fixture efficiency is not very good, 58% loss, or LOR of 0.58. So the overall system efficiency, when you multiply the source lumen by the LOR, gives you about 10 lumens per watt. Compact fluorescent could also suffer from quite poor performance, although the lamp lumens might be quite good at 60 lumens per watt. The fixture efficiency is very similar because it's a source that emits in all directions. LEDs themselves, though, actually have an advantage for things like downlighters in that they start off by being directional. All the light that you're measuring comes out of the front. All the heat comes out the back, which is why the fixtures look very different, but all the light comes out the front. So you might find actually you get a much bigger number than you would expect delivered out the fixture. So in this particular example, we've got a fixture efficiency of 90. There's a driver efficiency of 85, which is a reasonably good driver, and the thermal D rate is about 90% here. So you're actually getting 90% of the light out that you'd expect. And multiply that all together, you're getting a delivered efficiency of 69 lumens watt. Fantastic. Now this example is a number of years old, but it's true then as it is now. So okay. So then we're trying to say, right, okay, when you mash all this together, what you're really trying to work out is what light levels do I get in an application? And this was back to the point I was making earlier. If you go for something that's got too narrow a beam here for a general illumination, you get spots on the wall, so your average illuminance is poor. And this is typically what would a poorer quality LED fixture would do, or a poor quality design would do. They would claim it was a big beam angle, kind of like 60-degree beam. They'd actually make it 25 to kid you. And then you would look at it on the table and you go, wow, that's bright. If you put it in a room like this, you would find that your average illumination, you get shadows. You're going to get bright spots with lots and lots of gaps and shadows. Not a very attractive end solution. So good design of the fixture for the application is very key. Again, this is really kind of making the same point in a different way, but we'll run through it again because this point is really worth making. Let's take the light source, 65 lumen per watt CFL and 86 lumen per watt LED. Now the light's all coming out the LED at the front. CFL, it's omnidirectional. You get an LOR on the CFL about 70%. You get 90 on the LED. Multiply them together, your efficiency is considerably different, even though actually there's not a lot delta between the source lumens. When you look at the luminaire efficiency or the system efficiency, that's key. Now, that might mean to achieve a certain lux level, you would have to use a different number of fixtures in a different space. So actually, the most useful measure for lighting is really watts per meter squared normalized to 100 lux. Now, clearly, if the application is 500 lux, then you normalize it to 100 because that gives you the ability to compare energy efficiency. So this is a key number, and obviously we'll be coming on to conversations about Lenny at a later stage. Okay, so this is really about realistic performance expectations, and I suspect every one of you has seen a situation where you've seen a data sheet from a manufacturer that's actually got, like this, pick today. If you see a data sheet where the the fixture efficiency is written down as over 130 lumens per watt, then you will know that they're just using the LED number, and they haven't thought about all the other D-rate factors and all the other losses in the system. And that's one of the reasons, I guess, we would show our working out. So we'll give a source lumens, we'll then give a delivered lumens, and we'll give system efficiency. Because actually, we've seen from the thermal D-rate curves that we're losing a certain amount of light, so that would take us to this level. And then I guess we've got some optical losses to do with secondary optics, and bezels. That gets us down to, we're going optics only there. And then we've also got driver losses. Now, typically a driver might be as good as 85%. Some of them are terrible. We've seen drivers as efficiencies below 60%. We've seen them as high as mid-90s, which is pretty impressive. So when you multiply all that together, you get whole luminaire system efficiency. My rule of thumb is there's about, for economically sensible things, it's about 2/3. So if you've got an LED number there at 100, you'd be expecting 66 out. If you look at the 213 catalogue, we've got lumen LED efficiency numbers in the 130s. So we'd be expecting things, above 90 lumens per circuit watt for those. Okay, so I think it's pretty key. If you see sort of numbers that look too high and nobody looks like they've thought about these things, you'll see a lot of things just don't add up, and that's something to look for. Okay, let's talk about lifetime. Of course, the big challenge is, can you actually tell me for sure that a fixture will last 50,000 hours? Well, I guess the point is the LEDs that we're using today haven't actually been around for very long. They certainly haven't been around 50,000 hours. 1 year is 8,760 hours. So how anybody's going to know for certain that a product has been around 50,000 hours, is going to last 50,000 hours, is so really effectively what everybody's doing here is they're extrapolating from data they currently have. So we all know how LEDs age now. They will form a sort of a slow decay here. They age gracefully, if you like. So this is 100%. This is initial point in time. Then the speed at which, then they go down to 70. This is the point where your eye will notice the difference. If you put two side by side, you'll notice the difference. Obviously, if they abruptly change, you'll notice quicker. But you get the idea. This might be as long as 6,000 hours, or 10,000 hours, or 20,000 hours. This L70 number. What effectively we do is we will measure the fixture for a number every 1,000 hours and plot a graph. And you're getting little data points here every 1,000 hours. Okay? And that will allow us to extrapolate the performance of the system. Now, we'll come on to some of these things in the apples and pears guide later, and we'll come on to talk about this, how we actually specify this in the LILG guide. But this is the basic underpinning principle. We have to measure it every 1,000 hours. Now, at Photon Star, we've been measuring fixtures for over 4 years. So we've got history on all of these different generations of products. And we can say with confidence now that our fixtures probably will last 50,000 hours and probably longer. Because actually we haven't changed the build standard. We have changed the LEDs. We kept the same materials in there, so we know there's no gasket materials or thermal compounds in there that might degrade the LED faster than you would expect from its LM80 data. So we've got a high degree of confidence that the products are going to last. There's some Nemesis products there. They were first introduced in 2010, I think, or 2009, and 2010. So we've got data which is now 3 years old on those. So we have probably a little bit more confidence in putting our luminaire warranty up to 5 years than some who may have absolutely no idea whether the fixture will last or not. Okay, so lumen depreciation. There's a code here. Okay, so the other way of doing it is to look at how quickly something will depreciate. So we're going to do a test now, and we quoted at 25% of rated life, up to or a minimum of 6,000 hours. So we'll do the test at 6,000 hours, and we'll say, okay, how quickly does it decay? So if it's at 90% of initial light output, we can give that a category 1 or a code 9 against an IEC pass standard. And basically that will be a really superb bit of performance. At 80%, we're still pretty pleased with that. At greater than 70, I guess we would not be very happy with that at 6,000 hours, and certainly we'd be struggling to claim a lifetime data of anything more than 6,000 hours L70. So that would be a poor performer. But if the light output is 90% of initial, which is typical for a lot of the fixtures that we're testing, in fact, some of them actually have decreased by only, say, 6 or 10% over 6,000 hours, or even actually some of them as long as 20,000 hours. Now, one of the things we'll do with our 2013 range is, alongside it as a sales tool, we'll be providing reliability data for some of our key fixtures. This is going to be a key differentiator in terms of how customers see our product versus some of the newcomers on the market. We want it to last with a very good low junction temperature, and that means usually a decent sized heatsink, and ensuring that that heatsink perhaps doesn't run any hotter than, say, sort of 50 or 60 degrees. If it runs hotter than that, we'd be a bit worried. It would mean the junction temperature is getting a bit high, and as you can see, we would expect, as we run our fixture harder as well, that we would get reduced lifetimes there. Okay. So looking at this in more detail, let's define what we're talking about here. There's the ambient temperature in which the LED sits in. Here we go. There's the junction temperature there. That little tiny dot in there is where the light is actually produced and then gets put through the package and into the fixture. So I guess we would look at the T board and also then the heatsink temperature here. And it's pretty important also to understand that the ambient temperature will affect the LED lifetime as well. So that's another reason why you've got to keep the fixture well designed. A lot of people haven't thought that through. So again, the air temperature will impact the lifetime of the LED. So having a sealed cavity with LEDs is good from an IP point of view, and it stops other things attacking the LED, but we've got to make sure that the heatsink is at a low enough temperature, because the air and the heatsink will be quite close rated. So we don't want our heatsink temperature in something like a CS5 to go above 65, because actually this will also age the LEDs quicker than everybody will run. Again, this isn't a major point, but it just shows the level of depth and thought that has occurred in the design process for some of our best running and clearly most reliable products. Okay, so let's look at ambient operating temperatures. Of course, we have over-engineered a lot of our heat sinks. So as a result, we will find a situation where we can run them at higher ambient temperatures with slightly reduced lifetime, but still well in a comfortable place to ensure that they will work work well. And of course, that can have big benefits in terms of being able to use it with ceiling, sort of insulation and insulated ceilings, like, or in the Middle East or something like that. So I think the message we try to make is specifying LED luminaires, ask the questions. You've got to make sure your customers understand what they're buying. And what they're buying is a well-engineered product that they can rely on. They've also got to know what the pitfalls of not picking somebody who hasn't understood the basics of LED luminaire design. And you've got to look at the whole system, and you've got to ask questions all the way down the line. Now, this is really aimed at customers, and really it's really saying, look, it's your professional indemnity insurance. You know, are you really confident this is going to work? And I think this fear, and when people understand just how badly things can go wrong, I guess they go, wow, I definitely want to use PhotonStar with all that history, because actually there are some big challenges ahead for me if I pick something that isn't as good as that. So this is how we specify our products. We adopt the Lighting Industry Liaison Guide. It's backed by a large number of manufacturers, and it's also backed by all these professional bodies. Okay, since this presentation was actually written, the LIF and the LA have merged into the LIA, but it's backed by the Society of Light and Lighting, the ILP, the POBA, and the ILBA. Now, let's just really hammer home the key points of what this is about. It's about showing you're working. It's about being honest that you tested the fixtures. You've actually shown that you know what you're doing. And if you can present this data, somebody can feel confident they're going to get something that will last. Now, let's just look at this little graph here. This is one that we produced. Right. We've talked about the issues around lifetime fluid control gear, that's like drivers. We've also got issues around gasket and sealants. This is something that a lot of people have not understood in their fixture designs. We have. Basically, some of the materials you can use will actually attack the LED. So you'll get aging much quicker than you would expect. So, okay, great. So tick the box. You've got your thermals right. You've got your control gear well. You've picked good quality LEDs. Your optics are okay. Your PCB that you put the thing on there is great. Well, obviously, we do all our LED placements in-house at Contronics. This is another way in which we ensure that the quality is there too. So lots to get right. I think the analogy I use is the chain is only as strong as the weakest link. And any one of these things in this list could cause the whole system to fail. So it's about understanding it and having the confidence to specify in a specific way. Okay, thank you for listening.